Hi, I'm Brandon, and I will be presenting my project on 6D pose estimation. So why another pose estimation method? Well, when it comes to pose estimation with deep learning, there's two issues. First is illumination. Typically, you train your neural network via data collected with domain randomization or a physics-based renderer. But if you go into another scene, you have no guarantees that it will actually work within that scene. The other issue is, these methods actually don't provide a way to actually enforce constraints. So if you know the object is within someone's hands, like they're pinch grasping it, it would be nice that you can actually estimate the pose of the object such that it's constrained to be within contact of the finger pads of the human hand. The first part of this pipeline actually introduces a hybrid renderer. And so what the hybrid renderer does is it takes your object mesh along with information about your object and where it is in space. It renders it into intermediate form where a neural renderer can actually take that intermediate form and output a photorealistic image of the object. And this is nice because you can just use your standard photogrammetry setup, and you can either collect data in RGB or a illumination invariant source of information like an IR image from a time-of-flight camera. And this method allows you to have very photorealistic images. So the one on the left is the real image, and the one on the right is the rendered image at the same transformation. And rendering only takes 3 milliseconds. It is a hybrid approach. And you can take this neural renderer and you can generate a bunch of novel views. And once you have these novel views, you can train a global pose estimation method like this, where you take the object, you estimate the coordinates of the object in each pixel, and you use PNP ransack to solve initial transform. However, if you directly regress over the coordinates of the object, you get this blobby mess because it's actually regressing over the mean of identical locations on the object since it's highly symmetric. So the model in this work actually combines classification and regression by first classifying which area on the object you think this pixel belongs to. And then once you get a distribution of this, then you can go and you can force the regression to take one pose. And this is nice because before we had this blobby mess, but afterwards we actually get a clean coordinate regression of the object with a few artifacts. And that's fun if we have artifacts because we can take our differentiable renderer and our neural renderer and we can take the rendered image and the actual image, and you can calculate the difference between that, backpropagate it, and update your transformation so that you can actually do a local optimization of the pose, even if there's errors in the transformation. And by combining these two methods together in a highly occluded symmetric object like this, you can see PNP can have some errors when it's very occluded, like 15 centimeters, but then after performing optimization, you can actually reduce it to sub-millimeter accuracy. Thank you.